Hey, good morning. Yeah, with all this quarantine, I've been home watching the children most of the time. It's really hard to find quiet times for recording and doing lectures. That means they usually happen when either my wife takes the children out for a walk or something, or their nap time, or it's the middle of the night. I actually woke up at 4:30 in the morning for this guy, and I considered just recording then. I don't know what's wrong with me. I seem to be losing my mind here. Hey. But yeah, quarantine has me doing a lot of childcare. We watched a lot of Dragon's Rescue Riders, and yeah, it's actually not bad for like a show made for like toddlers. It's made off of the How to Train Your Dragon franchise, and it's written fairly intelligently. I don't know if it's actually Stockholm Syndrome, from watching it like 100 times over. It's just 2 short seasons.
Hi, Dada.
Hey, what's up, girl?
Good.
Yeah.
Yeah.
Yeah. Oh, yeah. Yeah, you see the baby there? Yeah. Anyway, yeah. So what are we gonna talk about today? So we went through all those lectures on metric spaces. Hey, Huggy. Huggy. Oh, come here, buddy. On metric spaces and Big O notation, and yeah, we haven't really been talking about that too much. So what I'd like to do is I'd like to take a look at these approximation schemes that we made for interpolation and approximation polynomials. Hey, dude. So I thought we could go ahead and talk about how we can turn these interpolation and polynomial approximation schemes into a Big O notation, which depends on something like their polynomial order and the number of samples you take. Anyway, so let's go ahead and take a look at that, and that's be a good lecture.
Okay, so let's go ahead and get started. So here I want to talk about how we can get Big O notation for Big O estimates for these various convergence theorems that we have. So thus far, so we have, say, polynomial approximations. And basically our goal is going to be to either show that the distance, the uniform distance, so sorry, not minimum, but the maximum difference pointwise over AB of the absolute value of f of x minus g of x. We want to say that this is a Big O of either, say, the degree of polynomial, or spacing h from, like, for Bernstein polynomials, or for interpolation or something like that. And so that's generally what we're trying to show. And so that that way we know if we increase the degree of polynomial, we can get a control over how big this is and hopefully make it go to 0. And ditto for this guy. So we have 3 different kinds of polynomial approximation that we looked at. So we have Taylor's series. I can't spell today, but series. We have also interpolating polynomials. And we also have Bernstein polynomials. I don't know if I'll get to the Bernstein polynomials this lecture, but we'll see. I might have to do a separate recording for that. In any case, so we had 2 convergence theorems for each of these. And so the one that we had for Taylor series used this remainder term. So we have, say, f of x minus the sum of j equals 0 to n of f jth derivative at a divided by j factorial times x minus a to j is equal to the n plus first derivative, so 1 past where this Taylor polynomial is, at c, for some c, at n plus 1 factorial, x minus a wherever it's centered, to n plus 1. Okay, so I think I'm using a different reference this time than I was before. It's the same formula. This is the Lagrange form of the remainder. And so ultimately, we want to be able to take this and get some sort of convergence rate out of it. What that's really going to amount to is getting a bound on this term here. We talked about it briefly, but I want to go in a little bit more depth. So that was that. And as far as interpolating polynomials, we had another theorem there. Don't worry, this will be the same one that I used before. Okay, so if we take a look, we have this one. F of x minus Pn of x is equal to f of n plus 1 xc divided by n plus 1 factorial. Then we have this product I going from 0 to n of x minus xi. So I think before I just had n plus 1 here, so let's change it back. So this will be n plus 1. It's going from 1 to n plus 1. Okay, so that was for when we had n plus 1 interpolation points. We're trying to find a polynomial of degree n that approximates it. So notice each of these requires high order derivatives. And the general principle here is that high order smoothness implies that we're going to have faster convergence. That's generally what it means. It isn't always true, but if you want to get higher convergence rates, you have to assume higher order, and that's particularly true with Bernstein polynomials. Where generally speaking, with Bernstein polynomials, the best you're going to do, the best you can do with just a continuous function is a big O of n to the square root of n, 1 over the square root of n is the best you can get for Bernstein polynomials with just continuous functions. But then if you add on, say, that they're continuously differentiable or that they have 5 derivatives that are all continuous, then suddenly Bernstein polynomial approximations converge a lot faster. Okay, so let's go on and talk about it. So starting off with Taylor series, put this back in blue. So okay, so we start off with the remainder, and remember we're trying to get a maximum of this difference, so maximum of x and a b. Really that's just going to mean that you take a maximum over the interval, so it's not going to change too much what we're talking about. So we're going to have f of x minus the sum, now I'm going to change this again on you, n equals, say, 0 to capital N, I like this better, f to nth derivative at where we're centered at over n factorial, x minus a to the nth power, absolute value is equal to f to the capital N plus 1 derivative at some c divided by capital N plus 1 factorial times x minus a to the capital N plus 1. Okay, so we want to be able to get some sort of bound here. So let's see what sort of assumptions we can make on the derivatives of f. So because if we didn't have this here, if it was just 1, then this would always go to 0 because it's basically an exponential divided by a factorial. So that would always converge. So what we're looking for then and since I put everything in absolute values, it should stay in absolute values, and this should be in absolute values. And let's also put the maximum out there too, just to stay consistent. So we're looking at the maximum of x in A, B. Okay. So now let's talk about some assumptions on the nth derivative of f. So if we talked about functions like, so if we talked about functions such as e to the x, sine of x, cosine of x, etc., we know that these are all roughly their own derivatives. And so, so basically, we can say that there exists an m bigger than 0, such that, basically, each, like say, e to the nth derivative, n plus 1 of c is less than m for all c in a bounded interval, ab, and all n. Right, we can assume that, basically because it's just going to give us derivatives of e, and well, e is bounded over a compact interval. This gives me either sine or cosine or plus or minus, and well, that's bounded over a compact interval. Ditto here, right? So that we can make that assumption, and that would work for that. But if we make even a small modification, we start running into a new problem. And so if I say, if we consider say e to the 5x, then suddenly I have a different problem. Then I have that f prime of x will end up giving me 5 e to the 5x. And if I continue, then I see that we're going to have f to the n plus 1 of x is equal to 5 to the n plus 1 times e to the 5x. And so here, there's going to be something that's uniform for all n, and so that's maybe a little bit of a problem. But what we do see is that there exists an m bigger than 0 such that f to the nth plus first derivative, xc, is less than m to the n plus 1. Right? Or even if I want, I can just say some constant, like say and c bigger than 0, such that we have this. So the constant would be the biggest value that e to the 5x takes on the interval, and this would be what we have there. We can keep finagling in this. I can put say a logarithm here, or something like that. But I can't. What I can't do is I can't give really good guarantees if I have this guy being a factorial, because then the factorial will kill this, and then this could possibly blow up, right? So that's what ends up happening with 1 over 1 minus x squared. It only works between x between say -1 and 1, because 1 over 1 minus x, which gives us the geometric series, basically gives us n factorial for our derivatives, and so then this has to be shrinking, and so the only way that happens is if the absolute value of x is less than 1, or at least the absolute value of x minus a is less than 1. Okay, so for these cases, let's just talk about exactly what we get from the Big O notation then. So I'm going to go ahead and this is the upper bound on our quantity. So I'm just going to go and copy that, and let's go to the next page. Okay. So we're going to assume that there exists a c and m greater than 0 such that f to the n plus first derivative xc is less than or equal to c times m to the n, right? And so this will cover e to the kx. It'll cover, basically e to the kx, or sine of kx, or cosine of kx, etc. Things like that. Okay. So then what do we see? Well, we see that we have then the maximum of x inside of AB. Let's say for all C and AB, just be explicit. All right, that C was known to live in AB, so then we can basically get a bound on that. So we're going to say that this is less than or equal to, we have C times m to the n, n plus 1, that's what we want over here, n plus 1, divided by n plus 1 factorial, times x minus a is going to be smaller than, say, b minus a, because we're assuming that little a is also in the interval, it's the n plus 1. Okay, and so then we have, since I already selected a bigger value here, I can just drop the maximum because I replaced x, and so it's just constantly inside now. So this is c times m to the n plus 1 over n plus 1 factorial times b minus a to the n plus 1. And I can continue writing this. I can say c times b minus a times m to the n plus first power divided by n plus 1 factorial. Okay. So this is just some quantity, and so I can call that something. So I'm going to say that c, and then we'll call this m tilde to n plus 1. M times m tilde to n plus first power divided by n plus 1 factorial, and it really is up to you what you do after this. But basically what we say is that the maximum now of x in AB of f of x minus the Taylor polynomial at x is equal to big O of, say, m tilde to n plus first power over n plus 1 factorial. And yeah, so then that's an idea of what you get. You basically get exponential over factorial, and we know that this goes to 0. Okay. Now, let's talk about something that's a little bit trickier. And so I messed up when I was talking about the convergence theorem for interpolation last time. And so I want to set this record straight. And so let's talk about this. So we have interpolation. And so let's see what we get. So here we had f of x minus, say, Pn of x is equal to, so the remainder term we got was fn plus 1 of c divided by n plus 1 factorial. Then we had a product I equals, say, 0 to n of x minus xi. If I put it, then I can put some maxes on it, and we can talk about our uniform metric. So I can put some maximum here, x over AB. So we want the biggest on this interval AB. So I'll put max x inside of AB, and then put absolute values everywhere. Boop, boop, and boop, and boop. Okay, so what do we got? So again, we're going to have some sort of business going on with our f, and for now, we're going to assume that f n plus 1 of c is less than or equal to m for all c in the interval AB and n. We can actually make exactly the same sort of assumptions that we did back here, but there was something different that's going on here that I really wanted to address, and that's what's happening with this product. Okay, so let's take a look at the product. so we have this product here, I equals 0 to n, or well, actually, in our notes, we're generally saying n plus 1 points and 1. So we'll say plus 1 and put a 1 here of the absolute value of x minus xi. So what is this product? Well, basically, this is a product where we take x minus x1 times x minus x2 times x minus x3 all the way up to where you have x minus xn plus 1. So there's n terms. Sorry, not n plus 1. Ugh, sorry. I'm screwing up here. Up to n. N plus 1 points. No, that's good. Yeah. That's what I want, right? That's what I want. Yes. Sorry, didn't get a lot of sleep last night. Okay, there we go. All right, so that's what we got. And so I need to get a bound. We want a bound on this. All right, so let's take a look at what we have. And we're going to assume equally spaced points. So we're going to assume that x1 is equal to a, x2 is equal to a plus h, x3 is equal to a plus 2h, etc. all the way up to xn plus 1, which should be equal to a plus n times h, which should also be equal to b. Right? So I'm saying that n here should be equal to b minus a over n, over h, or h should be b minus a over n. That's what I'm saying. Okay, so let's talk about it. So we have an a here, we have a b here, and we have a whole bunch of points. And I'm basically taking, so what this product is doing is I'm taking this point x, and I'm looking at all these distances. So between x and x1 is this, so x minus x1, or sorry, so too close, that's x2. So x1 was a, so this is absolutely of x minus x1, and this is, say x minus, it's going to be x minus x2, and this, sorry, gives me x minus x3, etc. Right, and then we're going to multiply all of those together all the way down the line, right? So x minus x4, etc. Okay, so what we want to do is we want to take all these ones, we want to basically get sort of an upper bound on each one of them. So if I take a look for this particular x, I see that this distance here is less than h, because this is h. So if I replace one of these terms, so if I replace this term here by h, it's actually going to be bigger. And if I replace this term with 2h, still going to get bigger. And if I replace this term here with, say, 3h, that is definitely getting bigger. And if I replace this term with, say, 4h, etc., and I keep going up, I'm ultimately going to have this. I get this. So I have this product where I going from 1 to n plus 1 of x minus xi. It's going to be less than or equal to the product of h times, let's say we started with 1, so hi. I going from 1 to n plus 1. So all down the line, we just keep expanding it over and over again until we get this, right? So now we want to talk about some way to get a bound on this term. And this is actually kind of fun. All right, so now let's examine the upper bound. And this is a typical thing you would do in numerical analysis. So, so we have hi, h and I are both positive, I going from 1 to n plus 1. Okay, so what I'm going to do is I'm first going to call this, call this ln, and I'm going to take the logarithm of ln. And what is that going to give me? Well, since it's the log of a product, I going from 1 to n plus 1 of hi, I can rewrite this as the log, the sum of the log of hi, I going from 1 to n plus 1. Okay, so now what I'm going to do is I'm going to multiply and divide by n. So I'm going to have, say, n, and I'm going to have sum of I going from 1 to n plus 1 of 1 over n log of h times I. Now this is really close to what I would have if I were to, say, take an integral, except I end up having one extra term, which is kind of annoying. So it's going to give me n times the sum I equals 1 to n of 1 over n log of hi plus an extra term that I need to peel off, and that's going to be the log of h times n plus 1 here. Okay, so now let's see what we end up getting there. So we have this, and this guy is the left-hand rule for an integral of a to b of, say, the log of x dx. This would play the role of, say, dt, and all we're really missing to get that is that we should multiply this by magnitude of a minus b, so that's properly h, which is what our delta t would be. So so then we can go ahead and rewrite this. Put this off on the side. So this is equal to n over absolute value b minus a times the sum of, say, absolute value b minus a over n log of hi. That's I going from 1 to n. And now we're going to have an extra term, plus we're going to have the log of hn plus h. Now what is hn? Well, we saw last time here that hn is going to be b minus a. So this is going to give me n over, or let's say this is approximately b minus a, and this is for large n, of the times the integral from a to b of log x dx. Okay. Now plus the log of b plus h. Now, as n gets really big, that's going to end up getting very, very small. And so this, again, can be thought of as being n over b minus a times the integral from a to b of log of x dx plus the log of b times, let's just say, log of 2b. So I'll just say this is less than that. Okay. So pretty close. So n over absolute value b minus a is going to be absolute value of b minus a is just b minus a. So this so far then is equal to 1 over h times the integral from a to b of log of x dx plus now what we're going to have is we're going to have log of, say, 2b. Okay, All right, so remember this was what we called L of n, and h depends on n. So that means, this is the log of this. So that means that ln is equal to e to the 1 over h, where h depends on n, of the integral from a to b of log of x dx, or is less than or equal to, I should say, plus log of 2b, right? And so I don't really care what this quantity is, it's just some constant. So we have e to the c over h times, again, another constant, say c tilde, because we just peel that off as a product. Okay, so now let's take it back home. So what did we get an estimate on? We got an estimate on this guy, which is the upper bound on this guy, which feeds into this guy. So if I take this here, and let's go ahead and copy. And 1, 2. Let's put it right here. All right, so now what do we get? So I can see that we have, let's put this in blue. So then we have the maximum of x inside of AB, and take the difference between f and its interpolating polynomial. Now this is going to be less than or equal to, we assumed that this was just constant, so we're going to have an m over, say, n plus 1 factorial. And now we're replacing this guy by e to the c over h times some c tilde. Okay. All right. So I was trying to work this in terms of being just h, but that's not going to work out because it's hard to see what's actually happening here. As h goes to 0, this definitely blows up to infinity, but then we have something going to 0 here. So we can make it clearer just by replacing h with its definition. So then we have m over, say, n plus 1 factorial times e to the, say, n over b minus a times c, and then times c tilde. Okay, that's a little bit better. So we see that this is growing like with n like an exponential, but this is shrinking like a factorial. So ultimately what we say then, because I don't care about this constant, I don't care about this constant, so what we can say then is that maximum value of AB of f of x minus Pn of x is equal to big O of, say, e to the n times c over b minus a divided by n plus 1 factorial. So all we care about are the things that are attached to n. C and over b minus a does affect how quickly this exponential grows, so that is actually kind of important to keep track of, or at least leave a constant in there. But basically we see that since this grows exponentially and this decreases like a factorial, this ends up going to 0. Okay. Maybe we can even replace this with this quantity. So we can just say we have e to the c over b minus a quantity raised to the n. So just some constant inside here that's raised to the nth power. Then we have an n plus 1 factorial here, and everything else is just constant. Some things that we can take from this is if we can relax this condition back over here, where I assumed that we had this, and we could actually replace it by something as like m to the n, or something like that. And that would be fine, just because that m would end up just being fed inside of here, because you would just split the exponent over those terms. So that's how you get big O estimates so far on Taylor series, and then also on interpolation. And the interpolation one was a little bit interesting because basically we had to turn this into a integral. So we took a product, and we don't know how to deal with products visually or like intuitively like that, but we do know how to deal with sums. So we took the logarithm of a product, and this is very standard in analysis. And we took that, and when you take the log of the product, then it gives you the sum of the logs. And so then that sum of logs, we multiply and divide by n, peeled off the term that wasn't just an nth term, and that gave us this. And then this term ended up being just an integral times n. This, for really big N, isn't going to really be that different from the integral, so we just replaced it with that. This is sort of an off-the-cuff estimate. What you would say instead is you would just say that for big enough N, this is going to be less than or equal to log plus epsilon for some epsilon, but still that ends up being a constant, and that's the only information we needed out of it. Then, once we were done and we had this estimate, we went ahead and took the exponential of this. This is something that you did a lot in Calculus 1, I think. And so then we ended up getting this bound. And then we end up having this. And this is really the quantity that we needed. We ultimately turned it back into an n and not an h when we got down to here, just because we needed to compare this with the factorial. But yeah, that's that. And yeah, that's how you got those. So now let's talk about Bernstein polynomials. I'm not going to go into too much depth, but I did want to talk about, basically what sort of convergence rates you should be able to expect out of them. It's a little bit more complicated and technical than the last two, so we're not going to go too deeply into it. Now let's talk about Big O estimates. For Bernstein polynomials. All right, and here we're going to have to make the assumption on f that it is twice continuously differentiable. All right, so that means that it can be differentiated twice, and the second derivative is continuous. Sorry if my handwriting is going to crap right now. Just, been writing for over an hour. So, okay. So let's take a look. So remember, if you recall, the nth Bernstein polynomial evaluated at x of f is given as the sum k going from 0 to n of n choose k times f of k over n times x to the k 1 minus x to the n minus k. Okay. Now, what we're going to do is we're going to take a look at this quantity. So we want to see the maximum of x inside of not ab, but 0, 1, because that's where the Bernstein approximation happens. You can rescale your functions to fit in there if you like. But so bn at x of f minus f of x. All right. And so that's what we're looking at. Ultimately what we have now is we get the maximum of x inside of 0, 1 of this. We get the sum k equals 0 to n of n choose k of f of k over n times x to the k times 1 minus x to the n minus k. Okay, and now we have minus f of x here. All right, so what I'm going to do now is I'm going to use get a Taylor polynomial of f of order 1. So that's going to give me a maximum x in 0, 1 of the sum k equals 0 to n of n choose k of, now we're going to have f of x plus not I, but k over n minus x times f prime of x plus f double prime of xi for some xi, and this depends on x, divided by 2 factorial, and then times k over n minus x squared, and this is times x to the k times 1 minus x to the n minus k minus f of x. All that absolute values. So now if I distribute this over to f and this onto f and I split that off on the sum, basically we know that the Bernoulli, sorry, not Bernoulli, but the Bernstein polynomials will end up just giving us f of x. Just because we know that Bn of x of 1, or any constant, is equal to just that constant. And so since k doesn't vary and f of x is constant with respect to n, what do we get? We get x 0, 1 is equal to the absolute value, we say f of x plus the sum k equals 0 to n of n choose k times k over n minus x times f prime of x, and this plus f double prime of xi at x over 2 k over n minus x squared, and x to the k 1 minus x to the n minus k. It looks like somehow I worked it inside over here. Just put it like that. Okay, and this minus f of x. All right, so this cancels that, and that goes away, which is nice. And so we have the maximum of x in, say, 0, 1 of this term. So we can split this into 2. We get sum of k equaling 0 to n of n choose k of k over n minus x times f prime of x times x to the k 1 minus x to the n minus k. Then we have plus f double prime of c depends on x over 2. And then we have the sum k going from, say, 0 to n of k over n minus x squared x to the k times 1 minus x to the n minus k. Boom. All right, so I'm going to take a look at these in 2 different chunks. So we take a look at this guy. My claim is that that should be 0. So here we go. Claim this is equal to 0. All right, it's not too bad to see. We had an identity that we worked out last time. We talked about Bernstein polynomials, and we saw that k over n of x to the k 1 minus x to the n minus k. So if I separate that out, this is just the the Bernstein polynomial of x of the function f of x equal to x, and that should just give us back x. All right. On the other hand, if we take a look at the sum of x times f prime, x of times and choose k of x to the k 1 minus x to the n minus k, we can actually factor out x here. We have n choose k x to the k 1 minus x to the n minus k, and this is the Bernstein polynomial approximate 1, so bn x of 1 times x. So this just gives me x. And otherwise, this doesn't depend on n, so I can go ahead and factor it out. So here we end up getting f prime of x times x minus x, and so that's equal to 0. All right, so good. So proof. All All right, so now we need to figure out what the rest of this is. So we just eliminated this, so that's gone. All right, so now we need to figure out this next term, and this is going to give us our convergence rate. Okay, so how are we going to get it? So what I'm going to do is I'm going to let m be equal to the maximum value of f double prime of x over for x in 0, 1. So we can just replace this with m, right, with an inequality. So I'll call this quantity star in absolute values. So I say a star is less than or equal to m over 2. And then we have the sum of k equals 0 to n of, oops, that should have had n choose k in here. Should put that back over here. N choose k. So we have n choose k of k over n minus x, but let's go ahead and write that out. So it's k squared over n squared minus 2x k over n plus x squared times x to the k, 1 minus x to the n minus k. Right? Okay, so that splits into 3 different sums. So a sum of n choose k of k squared over n squared times x to the k, 1 minus x to the n minus k. We get the sum of n choose k of 2x times k over n times x to the k, 1 minus x to the n minus k. And then we get the sum of x squared times, n choose k times x squared times x to the k, 1 minus x to the n minus k. And this goes from k equals 0 to n, k equals 0 to n, k equals 0 to n. All right. So, and for this can be pulled outside, and this can be pulled outside if we'd like. And so ultimately, this ends up giving us 2x, and then what's left over is actually just bn x for the function x, which is 2x and times x. This one, you pull out x squared, and it's just x squared times bn of x at 1, which is just x squared times 1. Okay, the only thing that's left here is this guy, and this gives us, we had this identity before, x squared plus x over n. Okay, so now let's put all these together. So we're supposed to take this term, subtract this term, and add this term. So let's see what we get. So we're going to have n minus 1 over n times x squared plus x over n. Then we subtract off 2x squared, then we add x squared. And so let's see what we get. So this quantity here is 1 minus 1 over n. And so let's see, so we're going to have minus 2 plus 1, so that's minus 1. And so then we end up having what's left over is that we have 1 over n times x squared plus x over n. Okay, good. That's what we want. So ultimately, everything that we have is this. We're going to take our function, the maximum of it, so this is a uniform norm. We killed this, and this term ends up being bounded by m over 2 times 1 over n times x squared minus x, or plus x. So let's put it all together. So therefore, we have the absolute, the maximum for x in, say, 0, 1 of bn x comma f minus f of x is less than or equal to m over 2 times 1 over n times we have x squared minus x. X squared minus x is x times x 1 minus x in absolute value. And so this quantity here, I think is bounded by a quarter. So, so this, in fact, is less than or equal to m over 2n times 1/4. And thus, maximum x in, say, 0, 1 of bn x f minus f of x is big O of 1 over n. And so, there you go. But that is assuming that f is twice differentiable. Say continuously differentiable. Okay, so I want you to see that. I'm not going to ask you to go and prove this entire theorem for the Bernstein polynomial in the exam or anything, but I do want you to know what it looks like, and I want you to know basically how you'd approach it. There are some identities I might ask you to prove, but not the whole proof itself. Don't worry. On the exam, I'll be very explicit leading up to it about what I want you to know. Okay, so that's 3 big O constants, big O convergence rates that we get for polynomial approximations using Taylor series, interpolation, and also Bernstein polynomials. And so, yeah, I think we should stop there.
Yeah. You want to tell them about big O notation? Yeah. Anyway, yeah. Hi. So that was big O notation. Yeah, I hear you, buddy. So that was big O notation. That was big O notation. And yeah, now you can see roughly how numerical analysts usually go about writing. Yeah, is that your doggy? Writing convergence results. Yeah, it looks like my children are getting a little restless. So maybe I should get going. But yeah, thanks for watching, and yeah, see you on the next lecture.
Hello, so
Yeah? You want to say bye-bye?
Bye-bye. Bye-bye. Bye-bye.